In this video, we'll be talking about Pascal's triangle and the binomial theorem. In the previous video, we discussed Pascal's triangle and its relationships to the values n choose k, where n choose k is the number of ways to select k objects from n objects, where repeats are not allowed and the order in which we select the objects does not matter. And so we saw that each value of Pascal's triangle, the kth value in the nth row, corresponds to n choose k, where we begin counting in both cases with 0 instead of 1. The binomial theorem states that for any non-negative integer n, the expansion of x plus y to the nth power is equal to the sum from k equals 0 up to n of n choose k times x to the n minus k times y to the kth power. So let's see an example of this for the value n equals 3. When n is equal to 3, we could expand x plus y to the third power, and we would have that as x plus y times itself 3 times. We can first multiply just x plus y times itself and get that quantity, and then multiply x by each of those 3 values and y by each of those 3 values. And now we can simplify our terms. So this simplifies to x to the third plus 3x squared y plus 3x y squared plus y cubed. So how does this relate to Pascal's triangle? Well, the coefficients of the values x to the third, etc., correspond with the values of Pascal's triangle. So the coefficient of x to the third in this expression is 1, and 1 is the same thing as 3 choose 0. So 3 choose 0 x to the third plus 3 is 3 choose 1 x squared y plus 3 is also the same thing as 3 choose 2 x y squared plus 1 is equivalent to 3 choose 3 y cubed. And so we see that the coefficients in this expansion are 1, 3, 3, 1, or 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. And note that this was the expansion of x plus y to the third, and this is row 3 of Pascal's triangle, where again we start counting with 0. So this is row 0, 1, 2, 3. So the binomial theorem tells us that the coefficients in the expansion of x plus y to the nth power will be the values n choose k, and therefore they will be the values in the nth row of Pascal's triangle. As one more example, let's look at the value n equals 5. And so we're looking at the expansion of x plus y to the 5th power. By the binomial theorem, that's going to be equal to 5 choose 0 times x to the n minus k. This is the k equals 0 term. So 5 minus 0 is 5, plus times y to the 0th power, which is 1, plus the k equals 1 term. That's going to be 5 choose 1, x to the 5 minus 1 is 4, y to the 1 power, plus the k equals 2 term. The k equals 2 term is 5 choose 2 times x to the 5 minus 2 is 3 times y to the 2nd power, plus the k equals 3rd term is 5 choose 3 times x to the 5 minus 3 is 2, y to the k equals 3 power, plus 5 choose 4 times x to the 5 minus 4 is 1 times y to the fourth power is the k equals 4 term, plus 5, choose 5 for the k equals 5 term, times x to the 5 minus 5 is 0, y to the fifth power. And so this is, again, the row of Pascal's triangle. The fifth row of Pascal's triangle are the values 5, choose k, for k equals 0 up to 5. So this is just equal to 1 times x to the fifth, plus 5, choose 1 is 5, x to the fourth, y, plus 5, choose 2 is 10, x to the third, y squared, plus 5, choose 3 is also 10, x squared, y cubed, plus 5, choose 4 is 5, x, y to the fourth, plus 5, choose 5 is 1, y to the fifth. So once we understand the pattern, we now have a really efficient way of expanding expressions of the form x plus y to the nth power. We can skip all the middle steps, and we know that the expansion is going to be of this form, where we have terms x to the n minus k, y to the k. In other words, the power of x starts as x to the fifth and then decreases down to 0, and the powers of y start at 0 and then increase up to the nth power. And the coefficients that go in front of those terms are the values in the nth row of Pascal's triangle. We're now going to do a proof of the binomial theorem. So we want to show that x plus y to the nth power is equal to the sum from k equals 0 to n of n choose k times x to the n minus k times y to the k. So let's look at the expansion of x plus y to the nth power. We've got x plus y multiplied by itself n times. And we know from our experience in algebra that when we multiply such a thing out, each term is of the form x to a power times y to a power, where the sum of the two powers is equal to n. So n minus k plus k equals n. And so yes, each term will be of this form. This is the most general form it can take. So we're looking for the number of terms of the form x to the n minus k, y to the k. How many of these terms will be of that form? Well, each such term is created by selecting n minus k of the x terms and k of the y terms. So in other words, we look at each of these elements of the product and we either multiply by the x or we multiply by the y. So the total number of terms of the form x to the n minus k, y to the k is equal to the number of ways to select n minus k of the x's from this set of products. And if we are selecting n minus k of the x's and we need to select n terms in total, then that means we are also selecting k of the y's by default. From each x plus y in the product, I'm only going to select either the x or the y. So I can't repeat my selections, and the order in which I select the x's or y's does not matter. So if I select this x and then that x and then that x, it doesn't matter whether I've selected them in that order or a different order. In other words, my selection is such that the order in which I select the objects does not matter, and I can't make any repeats. So the number of ways to select k objects from n objects, or to select n minus k objects from n objects, where order doesn't matter and repeats are not allowed, is n choose k. So we have proven this theorem. We've shown that the expansion of x plus y to the nth power is composed of terms of the form x to the n minus k times y to the k, and we've shown that the coefficient of each of those terms is n choose k, and therefore we are done. We've completed the proof. So let's do a quick example using the binomial theorem. So what is the coefficient of x to the 6th, y to the 7th in the expansion of x plus y to the 13th power? Well, we know from the binomial theorem that x plus y to the 13th power is the sum from k equals 0 up to n, which is 13, of 13 choose k, n choose k, times x to the n minus k, so 13 minus k, times y to the k. So we're specifically looking just for the x to the 6th, y to the 7th term. That means the k in this term is 7. So we're looking for the k equals 7 term. And we know that the k equals 7 term is 13 choose k equals 7, x to the 13 minus 7, y to the 7. So this is 13 choose 7, x to the 6th, y to the 7th. And we're just looking for the coefficient. So we're just looking for 13 choose 7, and we can calculate out what 13 choose 7 is. So 13 choose 7 is 13 factorial divided by 13 minus 7 factorial times 7 factorial. And we can calculate that out, either canceling out and multiplying or using a calculator, and we'd find that 1716 is the coefficient of the term x to the 6th, y to the 7th in the expansion of x plus y to the 13th. So let's look at another example using the binomial theorem. So what is the sum of the values in the nth row of Pascal's triangle? Okay, so the sum in the 0th row is just 1. The sum in the first row is 1 plus 1 is 2. In row 2 is 4. In the third row is 1 plus 3 plus 3 is plus 1 is 8, and so on. And you might see a pattern in these values if you add up the values in the row and see that these are each powers of 2. So 1 is 2 to the 0, 2 is 2 to the 1, 4 is 2 to the 2, 8 is 2 to the 3rd, and so on. So we've observed a pattern. Let's try to prove that it's always true. So the sum of the values in each row is equivalent to the sum of the values n choose 0 plus n choose 1 plus n choose 2 plus ... plus n choose k. That's the sum of the values in the nth row. So this is equal to the sum from k equals 0 up to n of n choose k, which looks a little bit like what we have in the binomial theorem, the sum from k equals 0 up to n of n choose k times x to the n minus k times y to the k. But of course there's a difference. Here we have an x to the n minus k and a y to the k. So are there some values for x and for y that we could choose, some specific numbers we could select that would essentially make this part disappear? So we shouldn't choose x equals 0, y equals 0. That would actually make the whole expression disappear. But we can use the multiplicative identity, which is 1 for each of those terms. And so that tells us that the sum from k equals 0 up to n of n choose k times 1 to the n minus k times 1 to the kth power will be equal to, by the binomial theorem, x plus y to the nth power. But here x is 1 and y is also 1 to the nth power. So 1 plus 1 to the nth power is just 2 to the n. And great, we have proved that the sum of the values in row n of Pascal's triangle is equal to 2 to the n, which is exactly the pattern that we observed.